Hello everyone and welcome to another video. So today I'd like to continue our discussion on dynamics and flight mechanics by talking a little bit about the flat earth equations of motion. So for those of you who've been following along with the discussion, you know that recently we've been looking at and examining the concept of different frames as well as velocity and acceleration in some of those different frames. So this might be a great spot to mention that what we're going to be talking about today is going to build off a lot of these other topics. So if you haven't seen some of these videos, please take a moment to make sure you've reviewed those and you're comfortable with some of these ideas, particularly the notation about how we're going to be talking about taking derivatives with respect to different frames and expressing vectors in different frames. So if you're okay with all that, the goal of today is, like I mentioned, we want to develop and derive what we're going to call the flat earth equations of motion. And really what we're doing here is we are trying to come up with a set of equations that are going to predict or allow us to simulate the dynamics of some rigid body moving in space. Now obviously our end goal is we'd like to try to model something like an aircraft, right? This being a flight mechanics discussion, I'm going to couch and frame a lot of the examples in the context of aircraft or aerospace systems. But what's interesting about the discussion today is that these flat earth equations of motion really, they're applicable to pretty much any rigid body moving through space. So really what we're going to do is you can almost think about it like we are going to model the dynamics of a rock, and it just is going to happen that we're going to see later on down the road that we can apply and change certain terms of the equation to make the equations for this rock behave like the equations for this aircraft. But really, like I said, at the end of the day, these equations should be valid for pretty much any rigid body moving around in some type of inertial frame. So if that sounds like fun, why don't we go ahead and get started? All right, so to get started, let's start real simply. So like we said, let's think about this rock, right? This rock is, I don't know, maybe some mass, m, okay? And if I want equations of motion of this, let's just go back to our undergraduate dynamics class that basically says if you've got this rock or this mass moving, let's make like some kind of coordinate system. Let's maybe call this like the x direction. Maybe I'll use a subscript I to denote that this is like an inertial x-axis, right? So we're going to assume that this frame is inertial. And all we're going to say is, well, if this thing has some kind of force acting on it, let's call this like, how about a force in the x direction, right? What's the equations of motion for this? So again, I think for those of you who have taken a undergraduate dynamics class, I think everyone is going to agree that, okay, the force is equal to the mass times the acceleration in the x direction, right? F is equal to ma, right? This is your undergraduate equation that I think everyone is comfortable with, right? And again, you could probably say that, all right, acceleration in the x, that's the same thing as the velocity in the x and its time derivative, right? Something like that. That's the exact same thing, okay? Now let's make this more interesting. How about instead of just being able to move in one direction, what if you have two dimensions? You know, there's an x and a y, right? So now you've got another force or a component of the force in the y direction. So I can do the same thing. I can say Fy is equal to the mass times the velocity in the y, its time rate of change. So in other words, the sum of the forces in the y is equal to the mass times the acceleration in the y, etc., right? And if you had a z, let me make sure I got that right. Yeah, x, y, z is coming out of the page, right? This is just Fz is equal to the mass times this, right? So again, nothing earth-shattering here. And again, instead of having these 1, 2, 3 sort of scalar equations, right? Couldn't you write this in just a vector expression? You could basically write that, okay, I'm going to write the force F, right? This is going to be the mass times the acceleration vector, right? Or I guess we can go write it like this, right? Or again, or we could write the force is the mass times the time rate of change of the velocity vector, right? Okay? So again, there is nothing earth-shattering about this, right? The only thing that maybe makes this a little bit interesting is, again, this is something we would have written down in our undergraduate dynamics class, right? And there's nothing fancy about it. Now, though, in the context of what we know about having different frames, some of these frames might be rotated with respect to one another. So we talked about this in our discussion about expressing vectors in different frames using rotation matrices, and we saw that you have to be a little bit careful with some of this notation, right? So if we wanted to, we could write all of this and express all of these in the inertial frame. So I could add a superscript I here and a superscript I on this vector, right? So really, the more accurate picture of this would be something like the force, right, expressed in the inertial frame is the mass times the velocity, right? Its time rate of change with respect to the inertial frame, right? So this is almost like saying we need to have our notation of this, right? We're looking at the time rate of change with the respect of the inertial frame, right? So I need a left superscript I, and then I need the left superscript, or excuse me, the right superscript I to say that it's expressed in the inertial frame I, right? So this is basically, you know, a very, well, I guess it's half simple, half a little bit more confusing, I guess the way we put it, with respect to just writing. This is basically just sum of the forces is equal to the mass times the acceleration, right? Really, this is kind of Newton's second law, right? And I'm going to put a little asterisk on this because really you're never going to get to the moon with F is equal to ma, right? Because that's not really what Newton's second law said, right? Newton's second law really said something like the sum of the external forces is equal to what? It's the time rate of change of the linear momentum, right? The linear momentum being mass times velocity, right? With respect to an inertial frame, right? Because the idea with an inertial frame was a frame in which this equation was true, right? So this is really Newton's second law, right? It just so happens if mass is constant, you can pull this out and then you end up with mass times acceleration, right? But this is probably the better one to be using, right? So really, all we have to do is just write down F is equal to F is equal to the time rate of change of linear momentum, right? Now, the thing that gets interesting now is a couple of things. So first thing that we need to do is what if we make the assumption that the mass is constant? So here's our first assumption that we're going to be taking, okay? So let's go ahead and assume that mass is constant. Right? So in other words, the object in question or the vehicle, whatever you want to say, it's not changing its mass, right? So again, this is why I said you're never going to get to the moon with this, right? Because to get to the moon, you're probably using a rocket, right? And a rocket definitely has a non-zero m dot, right? That's how a rocket operates, right? It is literally shooting mass out of its back end, right, at a non-trivial rate. So this is probably not a good assumption if you want to be writing equations of motion for a rocket or anything like that. But for our purposes, let's go ahead and assume that mass is constant. So again, this is like an electric aircraft or a glider or something like that. Or maybe it is like, you know, our 787 where, yeah, it is burning fuel, but maybe we can neglect that m dot because it's so small with respect to the actual vehicle size and the other dynamics that it's probably a second order effect. So again, long story short, this is just how we're going to justify that m is constant, right? Okay, if m is constant, then yeah, sure, we got no problem pulling this thing out, right? So mass can come outside. So then we have, again, F is equal to the mass times the time rate of change with respect to an inertial frame of the velocity vector, right? And again, if you compare this to this, they're basically the same thing, right? It's just this right now, I haven't expressed it in a particular frame. If you wanted to express it in the inertial frame, right, we recover this equation, right? So if this is what you want, we could stop here, right? This is actually perfectly valid equations of motion for a vehicle maneuvering in an inertial frame with a constant mass, right? So we could stop here if you wanted to, right? And again, this is basically what we would have done in a undergraduate dynamics class where we said, all right, that's fine. I'm going to assume that there's just this one frame here. I really don't care about anything else. I'm just going to talk about how this thing moves with respect to these axes, right? Now, the issue becomes is in a lot of situations, particularly for aircraft systems, what we're going to want is we're going to want to express the state of this or the velocity of this in terms of body components. So one issue, or it's going to be convenient for us, and we're going to say, how about, let's just say we want the velocity to be given as and we talked about this in a previous video, U, V, and W, right? And again, U was the velocity component in the body X axis, right? And then the same V was body velocity component in body Y, and then the W was velocity component in body Z, right? So we want to take into account the case where this mass, not only can it potentially translate, right? So not only can this mass move around, right? But it can also rotate, right? So the body frame of this system might not be aligned with the inertial frame of our reference point, right? So what we're going to want is this, and actually, I guess to be a little bit more explicit, we need to really have this superscript B, right? So we would want the state to be the velocity expressed in the body frame here, okay? So to do that, that's going to take a little bit more work. So tell you what, give me a second to erase some of this, and I'm going to redraw a couple of these frames. All right, so here's another view of what's going on, right? We've got some object or some mass, again, you can keep in your head it's a rock or an aircraft, whatever, but it is just maneuvering with respect to some inertial frame. So again, this is pretty much what we had earlier, it's just the only difference now is we've attached a body frame to this object that we want to have moving around, right? But otherwise, as long as this inertial frame is truly inertial, we should be able to write Newton's second law of how this object is maneuvering or translating with respect to this inertial frame, right? Now, the place where this gets a little bit interesting is, let's think about this for the case of, for example, us sitting here on Earth trying to understand how this aircraft or this object is maneuvering or how its dynamics are evolving with respect to us who are sitting on this inertial frame. So you can think of us as an observer sitting at this inertial frame, and we want to see, you know, under certain forces, if there's certain forces acting on this aircraft, how does the dynamics evolve, right? Is this aircraft going to go straight? Is it going to start curving? What's it going to do, right, under these different different forces, right? Now, the thing that makes this interesting is, again, let's think about this. If we are sitting here, we're typically usually sitting here on Earth, right? So we've got our globe, right? And we are sitting here at some location. So for example, me, I'm up here in North America, so I'm just gonna put my finger, I'm sitting here, I'm an observer sitting right here, and I want to see how this aircraft is maneuvering and what its dynamics look like as it's maneuvering with respect to me sitting here on this Earth. Now, the immediate warning sign that should be going off on your head is, as you know, Earth is actually not an inertial frame, right? This thing, as I sit here on Earth, I'm actually spinning around, right? So my frame is rotating, right? So Earth is not an inertial frame, right? The Earth-centered, Earth-fixed frame that I am sitting on, right? I am an observer on this planet, right? Which is rotating, right? And furthermore, not only is this Earth rotating, right? But it is also kind of spinning around the sun, right? At a rate of 1 trip around the sun every year, right? So the inertial frame, you know, depending on your application, you know, maybe it's safe to say the sun is an inertial frame, right? The center of the solar systems are inertial frame, but us sitting here on Earth, we're rotating and we're spinning around the sun. So there's a couple of other rotations happening. So our frame that we are sitting on, this might or might not be an inertial frame depending on your application, right? So you know, if we're just flying a little aircraft around on Earth, maybe it's okay to say that, well, why don't we assume maybe that Earth is not rotating? Let's make it stop rotating, right? And furthermore, another couple of things we can do. Well, you know what, tell you what, instead, we should probably write that down. So let's make a couple of assumptions. So here's another assumption, right? Let's go ahead and assume that Earth is not rotating. Right? So again, that is saying like the angular velocity vector of the Earth-centered, Earth-fixed frame with respect to the inertial frame or the middle of the sun or whatever we think is an inertial frame, let's assume that this is 0, right? Okay, so obviously this is not the real situation in real life, but this is one assumption we're going to have to make our equations of motion a little bit more manageable. Okay, so that is part of the battle. Now, the other thing that we're going to want to think about is, okay, if Earth isn't rotating and we can now be sitting on this planet, right? And maybe what we want to do then is we want to say that, okay, what if I could assume, can I safely assume then that the inertial frame is actually the vehicle carried northeast down frame? Is this a safe assumption to make? Why? I'm going to call it V. So again, remember, V is the vehicle carried northeast down frame. Or again, sometimes it's your local northeast down frame. So it's wherever the vehicle is, right, on your globe, say it's here in North America, the x-axis of this frame is always pointing north towards Santa Claus's house, right? The y-axis is always pointing east, and the z-axis, it makes a right-handed orthonormal Cartesian system, which typically is mostly pointed, quote unquote down. The reason I'm putting quote down in quotes, right, is because the Earth isn't actually a pure sphere, right? It's more of an ellipsoid as a better model. So this gets into the discussion of the difference between geocentric latitude versus geodetic latitude. So again, that's a little bit outside the scope of this, but again, I want to just mention that out there, that this is another thing to think about in some terms of some of these second order effects. Like, what if we want to assume maybe now that instead of the Earth being ellipsoid, let's assume, maybe for the sake of discussion for the next 2 minutes, let's assume the Earth is perfectly spheroid, right? So now you've got this northeast down frame, which is attached to the surface of Earth, and it's located at the center of mass of the aircraft, right? So now, again, we got to ask ourselves the question, is this northeast down frame an inertial frame, right? Is it non-rotating such that Newton's second laws should be reasonable within this frame, right? And again, this is another one of these situations where I can't say yes or no. It really depends on your application, right? What I mean by that is, consider a situation where, okay, let's say you've got your little Cessna 172 or some slow-moving aircraft that is flying around on the surface of Earth, right? Well, the northeast down frame, I better use my right hand because that's what we said. It's a right-handed coordinate system, right? This aircraft is probably not moving around Earth very quickly, right? Well, what does a Cessna do? 100 knots, 200 knots maybe at max, right? So this frame is really not moving because the aircraft is not changing location significantly or appreciably over the surface of Earth, right? Well, now, what if you swap this for something a little bit faster? Here's my 787. Okay, so as my 787 is flying along, actually, right, as it goes, in any direction, can you see how this is basically, it's rotating, right? Your northeast down frame is rotating, your latitude and longitude is changing, and the rate at which it changes is probably related to how fast you're moving. So again, now with the 787 example, maybe this thing is going fast enough that that rotation of the northeast down frame is, kind of maybe non-trivial. It's probably not zero, right? And again, if you up your example to now, what if you have like a hypersonic vehicle or something, like you got your space shuttle orbiting Earth, right? So now its northeast down frame, as this thing rotates around Earth, right? This thing makes a revolution. I don't know what the spaceship does, 30 hours or something like that, or maybe even faster, right? It goes around, and as you can see, the northeast down frame is moving and is rotating again. So again, this is another one of these situations where I just want to say, you got to think about some of these things and some of these assumptions. So what we're going to do is, let's go ahead and make another assumption right now, and let's say that the vehicle is not moving fast, or is not moving fast enough such that the northeast down frame is approximately not rotating, right? So again, let's just say the vehicle northeast down frame, so vehicle northeast down frame is not rotating, right? So again, that's equivalent to basically kind of making the assumption that the aircraft's speed is, appreciably slow enough for your application, okay? All right, so with that, I think we're kind of getting to that. And then finally, the last thing that we might want to do, and this is going to come in later, is let's assume that the Earth is effectively flat. We're basically going to assume that the Earth is a perfect sphere, which we're going to see later on is kind of equivalent to saying that the Earth is flat. So let's just go ahead and say Earth is flat. Flat, and we're going to see that this is basically the same thing as Earth as being perfectly spherical. Right? So for all of these assumptions we're making, flat and spherical, we're going to see have the same consequence. Effectively, we're going to see down the road this affects your gravity vector, but both of these are sort of equivalent from that perspective. So if all of these are true, right? We got what? All of these asterisks or caveats associated with our assumption so far, right? Not losing mass, right? Mass is constant. Earth is not rotating. The vehicle is not moving fast enough to make it the northeast down frame change appreciably, and we're going to assume it's all flat. If all that is true, then I think we're safe to say that the northeast down frame is an inertial reference frame, right? Okay, great. With all that preamble out of the way, now I think we're in a good spot to start developing our equations of motion. So if you remember from our previous discussion, we said, okay, we wrote down Newton's second law, right, for these assumptions. And we said, okay, the external forces are basically the mass times the time rate of change of the velocity vector with respect to the inertial frame, right? That's what we had, okay? So now what we can do is we can start writing this with respect to actually how is the velocity vector changing from the body frame. So in other words, what I'm going to use is, let's use our equation of Coriolis, right, which we detailed in this other video, right? We talked about the equation of Coriolis, which basically said that we can rewrite a vector, its derivative from the perspective of one vector, it's basically the derivative of that same vector with respect to the other frame, right? But then you have to take into account how the frames are rotating with respect to one another. So that was this, right? So this was our Coriolis equation, right? So great, substitute this into here for the VI term, right? So now what we have is okay, external forces is mass times V dot from the body frame plus omega b with respect to our inertial frame crossed with V. Right? Okay, now you can rearrange this. I want to solve this for V dot B. So if you do that and solve for V dot B, I think it's just going to take a little bit of algebra here, but you'll basically end up with this times F minus omega b with respect to I crossed V. Right? Great. And this here is our translational equations of motion, okay? A couple of things that we maybe should note. Because we made the assumption that the inertial frame is the same thing as the northeast down frame, for the remainder of this discussion and for this video, I may use these terms interchangeably. So frame I, or the inertial frame, is the same thing as the northeast down frame. So therefore, these subscripts I and V, I might use them interchangeably, but again, with these set of assumptions, that's going to be true, right? So if you ever see me write V for our flat Earth equations of motion, so for this discussion, basically you can assume that V means the same thing as the inertial frame, right? So let's examine this equation that we just developed, right? Now here we said that, okay, V, sorry, I maybe shouldn't have boxed this up yet. We should have expressed this in a particular frame. So let's choose to express all of these vectors in the body frame. So let's put a superscript right B on all of the vectors, right? Like that, right? Perfect. And now this is perfect because if you remember, we said that the velocity vector expressed in the body frame, right? That was UVW that we just talked about, right? So if you stare at this thing long enough, right, we could write this thing out as, in fact, let me come over here and I'll write it over here because we're going to probably want to start saving all these equations. We're going to see we're going to need to write a few more. But really, this term right here, right, that is basically, right, if you look at it, that is U dot V dot W dot, right? So this is the time rate of change of the velocity vector, right, is equal to, 1 over m times the forces expressed in the body frame minus omega b with respect to I expressed in the body frame crossed with the velocity vector here, which was UVW, right? So UVW, okay? So great. This here, you can basically see it sort of looks like, it looks a little bit like something from our differential equation discussion of we need something that looks like x dot is equal to f of x and, you know, basically control inputs or whatnot, right? This is the flavor, this is what we're trying to get to, is we're trying to get to equations of motion that look something like this. Well, this sure looks like it, right? You got x dot is equal to some function of the state x, but we also need to start examining this and this, right? So there's more terms in here, and this is one of these situations where you kind of, we can't solve this completely or to have a complete discussion right here, right now. We kind of have to keep going a little bit more on faith, and we're going to see, we're going to have to put together all of these equations simultaneously, and that's going to help us understand what is this term, right? In fact, we did talk about this in one of our previous videos, right? This is basically saying how is the body frame rotating with respect to the inertial frame or the vehicle northeast down frame, right? So in fact, that's our angular velocity vector that we already talked about, but we're going to see, we're going to need some equations that govern how this term evolves in time under different forces and moments, okay? So with that being said, with all that blabbing, I think this is a good equation to leave boxed. This is our translational equations of motion for our translational velocity. So maybe let's write that down because we're going to see we're going to need a few more. So this is our translational equation of motion, which is basically describing, right, translational velocity, right? Translational velocity, right? Because what it's telling us here is how the velocity vector dot is a function of all these other states, right? Okay, so now let's see if we can do something similar for, say, getting a rotational equation of motion for rotational velocity. Okay, so give me a second to erase the board and we'll get on with that. All right, so we took care of describing how this object can translate now with respect to the inertial frame. Now, what if in addition to just translating, this object can also rotate, right? So we need some angular rotation equations of motion to describe that rotation, okay? So just like we did for translation, let's go fall back on our good old friend Newton and let's write Newton's second law for rotation. Right? So if you remember, Newton's second law for rotation was very similar to the translation equation, right? So it basically said that now instead of the external forces, it's now the external moments, right, is equal to the time rate of change of, now instead of the linear momentum, it's the angular momentum, right? So I'll just write this as h here, okay? And again, we got to remember that this is the rate of change of this vector with respect to the inertial frame, right? So here's Newton's second law for rotation. And again, h, right, was the angular momentum vector, right? And the angular momentum vector is given by, just like, you know, in translation, the linear momentum was mass times velocity. The angular momentum is a similar idea of the idea of, you know, a quote-unquote mass or a moment of inertia times a velocity, right? But again, the thing that makes it a little bit more complicated for rotation is that the mass equivalent, which in this case is the inertia matrix, right? This is a 3x3 matrix, and now it's multiplied by a angular velocity vector, right? So this is, again, remember, this is your inertia matrix, okay, and this is a 3x3, right? And this is your angular velocity, right? So it does look similar to, in the sense, here's like a, you know, kind of similar idea of mass times velocity. So that gives us momentum, okay? Now, here's the interesting thing. We got to think about this. This matrix, right, it actually is measuring how the object resists rotation, but that depends on, again, the frame of reference, right? So the most typical frame of reference is this matrix here is expressed in the body frame of the vehicle, okay? then in that case, this angular velocity vector, this should be the body, how the body frame is rotating with respect to the inertial frame, right? So this is a good definition of the angular momentum, okay? So again, you got to remember, this is the inertia matrix of the expressed in the body frame. So this is attached to the body. And again, that is nice because then this matrix is constant, right? It's not changing. That's because, right, if we make an assumption that your rigid body or whatever object that we're trying to describe the dynamics of, as long as this thing doesn't have, you know, fuel sloshing around or things moving internally, if we just consider this to be a perfectly rigid body, right, its moment of inertia with respect to its body frame, right, which is rotating with the vehicle, it's not ever changing, right, because the geometry of this is constant, right? So that's nice, but we're going to see it's going to get us into a little bit of trouble actually right here, okay? So tell you what, let's plug this into this expression, right? So coming up here, what do we end up with? Let me rewrite this, okay? So we got some of the moments, the external moments is the time rate of change with respect to the inertial frame of the inertia matrix, right, which we put in the body frame, times the angular velocity vector, right, like that, okay? All right, now, here's where it gets interesting, right? If you look at this, we got to ask ourselves, is anything in here constant with respect to the inertial frame? So you can pretty much guarantee this vector is changing, right? This vector is changing all the time, right? If the vehicle is rotating, right? You know, at one point, if this vehicle is just doing this, if it's just like kind of, or here, let's say it's just moving like this, right? You can see that the angular velocity vector only has a component in the body y, right? But what if it was doing this? Now you have an angular velocity in the body x. And in fact, with respect to the inertial frame, depending on how this is oriented, right, this velocity vector could be moving all the time. I guess what I'm trying to get at, and again, I apologize for this, is probably my long-winded way of saying it, is this is not constant, right? So it definitely cannot come out of the derivative as you would kind of expect. Now, this is where it gets a little bit more interesting, right? If you remember with our Newton's second law for translation, what we earlier said is we said that the vehicle is not changing mass, right? The mass was constant. So in the translational part where this was just an m term, it was just plain old m, we could say the mass is not changing with respect to the inertial frame. And you could pull this out, right? Now, in this situation, though, you got to ask yourself the same question. Is this matrix, is the inertia matrix of the object changing with respect to the inertial frame? And actually, it is, right? Because if the vehicle is oriented like this, right? Right now, it's currently oriented like that. It has a certain inertia with respect to resisting rotation about the inertial x, inertial y, and inertial z, right? Now, if the vehicle is in a different orientation, suddenly its ability to resist rotation with respect to this inertial x, the inertial y, and the inertial z has changed, right? So we've got a little bit of a problem here because I can't even take this matrix out of the derivative operator because it is changing with respect to the inertial frame. It is not constant with respect to this derivative, right? Now, what we can do though is the problem was this with this thing I, right? We're trying to ask what is the change of this vector with respect to the inertial frame I. Well, if that's too much for us to deal with because of this problem, let's change it. It would be great if I could ask how is this vector changing with respect to the body frame, right? So again, let's do a Coriolis, right? So let's go ahead and apply Coriolis equation / theorem, right? Which basically is going to allow us to rewrite this, right? So this here is asking, let's just, did I actually write that out? Yeah, I guess what we can do is let's just do the same thing here. Mass, or excuse me, external moments is, now this is effectively, how is this vector changing with respect to I? Well, I can use Coriolis to say that is the same thing as how is that vector changing with respect to B, right? plus now I got to take into account how these two frames, B with respect to I, is rotating with respect to the original vector. So with respect to I cross omega B with respect to I, right? So that's just Coriolis, right? So I changed the perspective of this, this vector derivative to be with respect to the other vector, or this vector with respect to the other frame, and then I take into account the other component via Coriolis, right? Okay, so now let's look at that. This is a lot better because now, look at this. This is asking, how is this vector here changing with respect to the body frame? And now you can see that, okay, this is great because if we make the assumption that the geometry of that object is fixed, right? If it's rigid, it doesn't have any wings that are sweeping back and forth, it looks the same with respect to the body frame, right? The inertia matrix is never changing with respect to the body. Now this IB can come out of this derivative operator because again, this inertia matrix is constant with respect to the body, right? So now I can pull that out. So now I end up with IB, right, times ddt with respect to B of omega B with respect to I, right, crossed omega B with respect to I, crossed with IB omega B with respect to I. Yikes, it's a lot of ways. Okay, and again, now what we can do is let's solve for this term right here. I want to isolate this because this is effectively, it looks like an x dot, right? This is like the state vector dot. I want that to equal something. So again, all I got to do is move this to the other side, invert the IB to get everything on one side, and tell you what, let me just write the result, right? It's just algebra at this point. So move this over to the other side, move the m to that side, hit left multiply by IB inverse to isolate, and we end up with ddt with respect to B of omega B with respect to I, right, is equal to the whole quantity, again here, IB inverse times the quantity of the moment minus omega B with respect to I crossed IB omega B with respect to I. Great, there we go. And again, if we go ahead and express all of this in the body frame, we can add superscript b's to the right side of all these. So write superscripts on all these. So I'm going to say express this vector in the body frame. This is the vector, it needs to be expressed in the body frame, expressed in the body frame, expressed in the body frame, like such, right? Great. And now at this point, if you look at this, this is basically Newton's second law, Newton's rotational, right? So this is our rotational equation of motion, which is describing the rotational velocity, right? So this is doing rotational velocity, right? It's describing how the rotational velocity changes, right? So again, what we can maybe do is let's collect this over here. Examine this left-hand side, right? This is, how is this angular velocity vector changing with respect to the body frame? So this is actually, right? This is PQR dot, right? So again, you remember, P was the angular velocity vector in the body frame, Q was the angular velocity vector in the body Y, and then R was the angular velocity vector in the body Z. So this thing over here is actually these time rate of change dots, right? And again, this is expressed in the body frame, is equal to, then we just got to write down that whole other side, right? And so it's IB inverse times the quantity, the external moments expressed in the body frame, minus omega B with respect to I, expressed in the body frame, crossed with IB times omega B with respect to I. Like that. There we go. Great. So look at this. We're getting even closer. So now we have our translational equations of motion tell us how the translational velocity evolve. We just now got an equation of motion which tells us how the rotational velocities evolve. Okay. So the last thing we need to do is now look at we need a translational equation of motion which tell us the translational position, and we need a rotational equation of motion, which gives us the rotational position, right? We just did the two velocities. Now we need two positions. All right, and luckily for us, these next two set of equations of motion, we actually already covered them in other videos. So let's start with the rotational equations of motion for the angular position description, right? So we already talked about that in our video discussing the Euler kinematical equations and Poisson's kinematical equations, right? And what we saw there was that was this equation of motion right here, right? It's basically, I mean, again, we call this the Euler kinematical equations, but it really is a set of equations of motion which tell us how the Euler angle time rates of change are related to other states of the system, right? Namely, the Euler angles phi, theta, psi, and then the angular velocity vector, right? Omega b with respect to, and again, remember, v is the same thing as I in our discussion, right? So these, this is basically a good set of equations for describing the angular position, how it evolves with respect to time. So again, what we can do then is basically just, again, capture this and collect this equation of motion, right? We can box this up if you want to be consistent with our previous notation and write that over here. So again, the thing on the left, right, that is the time rate of change of the Euler angle. So that is phi dot theta dot and psi dot is equal to, it's just this matrix, right, the Euler kinematical equation, so we're just going to write this as h of phi, right, times omega b with respect to v, expressed in the body frame, right? So great, there are three equations of motion for the angular positions, and then our translational equations of motion, that was described in our video where we discussed the navigation equations, right? That was how we basically compute position north, east, and down. That's what you end up with this equation over here. So again, same thing. Sure, if you want to box this up to be consistent, I'm going to assume you've watched those other videos and we can use them just right here. So again, let's just copy that down. So again, if you look at the left side of it, that the velocity vector expressed in the vehicle northeast down frame, well, that's just the position north dot, position east dot, and the position down dot, right, is equal to, it's just the direction cosine matrix rotating from body to vehicle northeast down frame, and we saw that was a rotation over all three Euler angles, phi, theta, psi, and then I just need to multiply by v expressed in the body frame, which was actually UVW, right? So I guess the other way you could write this is UVW, right? Which is kind of what we did over here. So I guess maybe to be consistent, maybe we should do that as well. I guess we can write this as times UVW, right? Okay, so there you go. If you look at this, here is our complete set of equations of motion, right? You know what? Give me a second to erase the board here, get some whiteboard space, and let's collect all of them together in a nice closed form set of equations. All right, so I think we're in a real good position to basically collect all of these equations of motion into a single consistent set of 12 equations of motion, or basically 12 nonlinear ordinary differential equations. So again, the first thing we need to do is choose a state vector. So the state vector we're going to choose is, first, we're going to put the translational velocities, or at least three quantities which represent translational velocities. We are going to choose velocities in the body frame, right? So that's UVW. So these first three here are basically VB, right? Then the next three states are going to be three pieces of information, or three signals which represent the angular velocity of the vehicle expressed in the body frame. So that's P, Q, and R. So again, these three represent this, right? The next three are the angular positions, right? So that is phi, theta, psi, which we kind of called this triple element. Again, I don't want to call this a vector, right? Because you remember from our discussion of the Euler kinematical equations, phi, theta, and psi, this is not really a vector, right? These are three Euler angles with respect to different frames. So that's why I don't have a bar on this, because I don't want to say this is a vector that can be expressed in any particular frame, but it doesn't really matter because these three are still just representing the next three angular positions, right? There is nothing that says they have to be expressed in a consistent vector. We just have three signals here again, right? So here's our three Euler angles. And then lastly, our three translational positions, position northeast down, that is the position of the vehicle expressed in the northeast down or the vehicle carried northeast down frame V. Okay, so here we go. We have states 1, 2, 3, all the way through 12. This is what it looks like. So now what we can do is, if this is our state vector, let's rewrite our equations of motion with respect to these states and see what happens. And what happened to this thing? Sorry, wait a second. I'm missing a bunch of signs here. Sorry. I just noticed this thing. There should be a minus sign here, and this is a cross product, right? Sorry, I don't know how that got so messed up, but anyway, I think I messed it up when I was transcribing it over here. We derived it correctly. This is what it should look like again. Remember, this was our Newton's second law for translational velocity got us this set of equations of motion. So now let's rewrite this. So if you look at this thing long enough, right, you can basically say that that is, what do we have here? U dot, that is x1 dot. So we have x1 dot, right? x2 dot, x3 dot, right? This is this term right here, right? So this is equal to 1 over m times the external forces expressed in the body frame minus, okay, what is omega b with respect to I? That is these three quantities or the next three states. So this is basically just what? x4, x5, x6, right? Crossed with UVW, which again was states 1, 2, and 3. So crossed with x1, x2, x3. Great. Okay, so there's our first set of equations of motion. Let's go about how do we get equations for x4 dot, 5 dot, 6 dot? Well, that's what we wrote right here. This was Newton's second law for rotation, right? So if we get x4, x5, x6 dot, 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 right? This quantity, this is just this right here, okay? So that apparently is equal to, what do we have over here? IB inverse times the quantity, the moments, right, expressed in the body frame, minus, again, we know now what omega b with respect to I is. It is just P, Q, and R, or for x4, 5, 6. So this is minus, yeah, here we go, x4, x5, x6, right? That vector crossed with IB, our moment of inertia matrix, crossed with that same vector again, right? x4, x5, x6. Great, end parentheses. Great, great, great. Okay, and then let's keep going here. Okay, now we need x7, x8, x9 dot, right? And again, if you stare at this long enough, we said that is phi dot, theta dot, psi dot, which is exactly what we had here with our Euler kinematical equation. So this is now just h sub phi. And again, phi is the same thing as x7, x8, x9, right? So this is really, this matrix is a function of only x7, x8, x9, right? That times omega b with respect to v, which we said in this case is the same thing as omega b with respect to I. So this is again times x4, yeah, 4, x5, x6. Okay, great. And then lastly, we just need x10, x11, x12, and we need their dots, right, or their time rate of changes, right? And again, this is P northeast down dot, which is what we just derived over here. So that is just this giant rotation matrix from the body to the northeast down frame, which again, we see is just a function of the Euler angles, or it's a function of x7, x8, x9, times UVW, which is actually x1, 2, 3, right? So this is times x1, x2, x3. Great. now this is awesome, because if you look at this, what have we got on this entire left side? If we write this instead of, instead of writing this as 4 sets of equations, you know what? Let's just write this all in one big giant vector, right? So I'm just going to kind of combine all of these like this. Okay. I'm just going to put a big, right? This is just a vector, right? Okay. Is equal to, and I guess I can get rid of these 4 equal signs. I just need 1 equal sign, because I'm just going to stack all this together in a big vector, right? There you have it. Now, look at this vector, right? This is x dot, right? And this whole thing on the other side, so we have now x dot is equal to this whole thing over here. It's complicated, I grant you that, right? But it's nothing more than just some function, right, where you tell this function the states x1 through x12, and you also tell it some other small information like the mass, the moment of inertia, and these terms are are deceptively simple right now, but those are going to give some richness and some interest in a second. But long story short, this whole thing over here looks a whole lot like it's just some complicated function of the states, right? And we are going to see in a second that actually what also weasels its way in here is the control inputs, or whatever external inputs go into your system are going to weasel their way into these equations of motion, mostly through the F and the M expressions. But long story short, we did it. We derived this set of equations of motion, right? So what's so great about this is now that we have this giant F, right? These are what are referred to as basically the flat Earth equations of motion, right? So this is, if you look up Stevens and Lewis, right, our aircraft simulation and control book, I think you go to page, I wrote it down here at some point. Shoot, don't tell me I forgot to write it down. It's like page 50 or something like that. But again, they refer to this as the flat Earth equations of motions. This is what it is, right? And think about how we got here. What this thing does now, right? What we're going to be allowed to do now is, if we have this F, what we have is you basically are going to implement this. Then here's this function, right? It has inputs of the state vector and some external controls, deflections. Again, we're going to see how this U enters in a second, right? What this thing computes is x dot, right? Now, if we go ahead and integrate this, numerically integrate this, out comes the state, right? Now, if you wrap this back like such, right? Now, you box up everything within sort of this pink line, right? Now, you basically have a I keep wanting calling it an aircraft, but again, you got to remember this set of equations of motion is valid for any object moving around with respect to an inertial frame in this flat Earth sort of scenario. So this is basically your vehicle, or again, it doesn't have to be a vehicle, right? It can be our rock floating around, right? It can be your meteorite floating through space or whatever, if you wanted that to be the system. You know what we should have probably called this? We should just call it the system, right? It's your system, right? Your system has inputs U, and out comes the state vector X, right? So this is awesome. This is exactly what we want to do. It's going to open up a lot of possibilities as soon as we can describe this F, right? And here it is, right? And again, the reason this is so exciting is because take a look at these set of equations of motion, right? These are the flat Earth equations of motion, and it's totally general, right? Nothing here says this is an aircraft. Nothing here says this is a meteorite or a robot or a boat or anything, right? It's pretty much valid for anything. Now, with that, again, the reason we can get away with that is there are several terms in here which can make the problem, or can make these set of equations of motion problem specific. In particular, right, like I said, if you stare at this term is definitely vehicle specific, the mass. What is the mass of the vehicle? You definitely need to know that. So that will change depending on what you're trying to simulate or predict. Same thing with the moment of inertia matrix, right? Depending on the geometry of this object, that moment of inertia matrix is going to be different, right? Now, the only other things that work its way into this are this term here and this term here, right? And you got to remember, this thing is, what is it? This is the external forces in the body frame. And this is why this equation of motion is it's kind of deceptively simple the way it's posed, right? It looks like you can write it down on one page, but these forces can be extremely complicated, right? Especially if you have something like an aircraft, right? These forces could be a function of the aerodynamics, the propulsion, gravity, all these other things that could be affecting the forces are going to enter into. So this term is definitely non-trivial. Same thing with the external moments, right? So with that being said, I think what we want to do is we want to dedicate some time looking at some of these equations of motion and some of these terms in it and think about what can we do, or how are these going to be different for our different systems? So I want to, let's pause here, because again, I want to belabor the fact that these are your general class or general formulation of the equations of motion for your flat Earth system. We are going to get now into some of these other ones. So again, keep in mind, this is general. This works for pretty much anything, right? This is not aircraft specific. But what I want to do immediately next is let's talk about how some of those terms might change if you had a specific system, for example, like an aircraft. And also we'll look at which of these terms, is there any other interesting sort of behavior in these equations of motions that we might want to think about? So give me a second to erase some of the board. I'll let you pause and let the gravity of this sink in, because again, I do want to just keep and continue stressing the fact that these are good equations for basically any rigid body operating with respect to an inertial frame. All right, so one of the first things that we can talk about that make these set of equations of motion specific to a given vehicle is this signal U, right? These are the external, what I keep calling control inputs or external inputs, control surface deflections, however you want to think about them. They are something that come into the system which affect the equations of motion, right? But what's a little interesting is, if you look over here, you don't explicitly see a U showing up, right? The reason why is we're going to see that U is going to affect terms like the forces and the moments, okay? And the reason why is if you think about what this signal U represents, again, I always think it's easiest to look at a concrete example. So let's go back to our aviation example of an aircraft, right? And typically this signal U is things that say the pilot might be able to influence. So for this, 787 model, let's simplify it and just say, there are things like, what can you deflect? There's like an aileron. Maybe let's call this like a deflection of the aileron, like a delta aileron, right? So the ailerons are going to make the aircraft roll. What else is there? There's probably elevators in the back. So maybe let's call this, how about a delta E for delta elevators? There's a rudder, right? The rudder can make this thing yaw. So there's like a delta rudder. And then there's two engines here, right? A left and a right engine. And the pilot probably has independent control of the throttles to both engines. So I don't know, there maybe is like a delta throttle 1 and a delta throttle 2. Okay, so if you just start listing all of the control surfaces that can be deflected or controlled on this vehicle or this system, you might stack all of these into a vector, right? And let's just call this vector U. Okay, and then the other name you can say is instead is let's just call this U1, U2, U3, U4, and U5. Okay, so for this particular aircraft, the control input vector is obviously tailored to its specific configuration, right? You could start tacking on more and more and more of these. Like there's probably spoilers, there's slats, there's flaps, there's all kinds of different other things that you might be able to add. But for a simple model, I think this is probably sufficient, right? So you can easily see why this is specific to your given system, because again, if you change it, like instead of an aircraft, what if you had something like this, like a multi-rotor or something like that, or a quad-rotor aircraft? So in this case, I've got 4 engines. So this vehicle, if I'm trying to write equations of motion for this, these are still the appropriate equations of motion as we discussed, but this input control vector is different. So for this example, U for the quad rotor, you know, in this case, there's no ailerons, elevators, or anything like that. There's just simply 4 motors. So now you might have like a delta throttle 1, delta throttle 2, delta throttle 3, and a delta throttle 4. So in this case, there are 4 inputs, and they're completely different, right? And what we're going to look at next now is, now that we have a good idea of what this control vector is, or this U, you can probably start to see how these control inputs are going to affect this term F, right? Because obviously if you crank up the motors, the force goes up, and you know, we're gonna have to work out which direction it's in, right? Because we have to express this in the body frame. But you can see how if you change that control vector U, you're basically changing this term F, right? And similarly, you're also changing the moment vector, right? Because if I actuate these motors in different asymmetric thrust levels, right, you probably are going to get some type of moment which is going to tilt this object in different directions, right? So great. I think the point that we want to take away is, now that U, it obviously works its way into the equations of motion, even though they're not explicitly listed here. We're going to see that F and M, these are basically functions of both the states and the controls. So tell you what, let's take a look at these 2 terms next. All right, so let's start with this term FB, right? So we said this is basically the sum of all of the external forces on the object expressed in the body frame. So it might be helpful to break this up into several different independent terms. So why don't we look at this as the sum of, how about all of the forces due to gravity expressed in the body frame, plus all of the forces due to, say, like the engines or propulsion expressed in the body frame, plus all of the forces due to, say, aerodynamics in the body frame. And now, as you can kind of see, we're starting to make this, again, a little bit specific to our vehicle. So you can kind of see this is probably like an aircraft or an aerospace system, because we care about the aerodynamics, but really almost anything that's traveling around in Earth's atmosphere probably has aerodynamics. You probably have some propulsive force, and you're probably subject to gravity. So this is still kind of, you know, it's got halfway vehicle specific, halfway still completely generic, but I think this is good for now. Let's look at each one of these terms in turn to see what they sort of look like. So starting out with the gravity, right? This is a little bit where we're going to see where it was helpful to make this flat Earth or perfectly spherical Earth assumption, right? Because if we make the assumption that Earth is perfectly spherical, right? Okay, and you've got your now northeast down frame, right? So here is your X northeast down, Y is, I guess, going, I think it's going into the board, right? So here's Y, and then here's Z, right? Okay. So if this is the case, you know what? It's actually really easy to express the gravity force in the northeast down frame, right? Because which direction is gravity pointing? Gravity is just going to be pointing straight down, right? So your gravity vector is just, whoops, I should have drawn that. I'm trying to draw it aligned up with this. Sorry. With the Z. Right? So really what you're going to see is the gravity vector, right, can be easily written as this, 0, 0, mg, right? This is the gravity force expressed in the northeast down frame for our flat / spherical Earth, right? Now, the reason why I want to bring this up is you know, what if this was, you know, we use an ellipsoid model of Earth, which is maybe a little bit more accurate, right? So if there was an ellipsoid, now you've got your north, here's your X north, your Y north, east down and your z northeast down frame, right? So now the slight problem with this ellipsoid model is if you assume the CG of Earth is in here, you now see that the gravity vector is not necessarily aligned purely with the down axis, right? So this would have some non-zero terms potentially in these locations, and their amounts might change depending on where you're located, right? So this is why this model is a little bit more complicated. So let's go with our flat / spherical Earth so that we can get away with this very easy expression of gravity, right? So if that's the case, what's nice about this is it's actually really simple then to get the gravity force expressed in the body frame, right? The way we do that is, well, we have the gravity force expressed in the northeast down frame. So all I need to do now is rotate from the northeast down frame to the body frame, and this is just the direction cosine matrix basically over your Euler angles that we already discussed, right? And that actually showed up. It's this same, well, I guess it's technically the transpose of this matrix right here, but for all intents and purposes, you can see we already have this thing. And what's nice about this is, yeah, you saw that this was a full 3x3 unitary matrix, right, which was filled all over with sines and cosines. I don't want to write it down in the interest of time here. Maybe I'll just flash a screenshot of what it should look like over there. But you see that this gravity force, this is 0, 0, then something. So basically, you only care about the third column of this when you do this matrix multiplication. So this actually turns out to be really, really, well, I guess not really, really simple, but by the time you do that matrix multiplication, you end up with just something that looks like negative sine of theta, which was just x8, and then sine of phi, which was x7, times cosine of theta, which was x8, and then cosine of theta, which was just x7, and then cosine of phi, which was x8, right? So here you go. So here's the gravity expressed in the body frame. It's a nice closed form solution, and now you can see that the gravity force is a function of just the states, right? Namely, it's just a function of your theta and phi, right? Of two Euler angles. So really, maybe the other way we could write this is we could say your F gravity in the body frame is really a function of the states, right? Which is perfect because we are trying to get this entire set of equations to be a function of just the states and the controls, right? So there you go. There's gravity force. Okay, how about the engine? All right, so now let's take a look at how the engine, or I guess maybe more generically, the propulsion of your vehicle enters into the expression. So that's this term here that we called FE expressed in the body frame. That's what we're looking for, right? And this you can easily see is definitely vehicle specific because the propulsion systems of your different vehicles are completely different, right? So again, let's go back to our 787 example where you've got two engines on board, right? So this engine expression, I guess if you look at how the engines are aligned, they sure seem to look like they're aligned with the body x-axis, right? If you increase the thrust, you basically increase the forward force on this vehicle, and assuming that these things are perfectly aligned with the body axis, maybe what we can do is you can write a really easy expression of this. It's really, you know, let's call this F propulsion 1 plus F propulsion 2, and then 0, 0, right? So here's the propulsive force from engine 1 plus the propulsive force of engine 2, and they're all aligned in the x body axis, and there's nothing in either other direction, right? Now, again, if you look at these two forces, the force that each engine is producing is probably directly related to the throttle, right? So again, let's assume a really simple model where we'll say the force of the engines is directly proportional to the throttle. So for example, we could do something really simple like, I don't know, how about this first engine? Let's assume this first engine can provide the thrust of, I don't know, half the weight of the vehicle. So something like mg over 2 times delta throttle 1, right? So here's the force that the first engine can produce, and then plus mg over 2 delta throttle 2, right? So really what you can do is we could rewrite this, right? Remember we said that these two throttles, I guess we should have written down our control vector, right? U was, I think we said this was delta aileron, delta elevator, delta rudder, delta throttle 1, delta throttle 2, right? That was the control vector we had earlier. So again, you could rewrite this whole thing as, I guess if you collect terms, this is what mg plus u4 plus u5. And I guess it's actually, no, to mg over 2. There we go, something like that, right? 0, 0, right? Great. So now if we assume that your throttles like U4 and U5 are in the range of, I don't know, like say 0 means off and 1 means full throttle, right? So in this really simple model, you can see that when both engines are spun up completely, we basically have a propulsive force equal to the weight. So this is like a system where we're saying the thrust to weight ratio of this vehicle is 1 at maximum. So this thing theoretically, I guess, could hover, but maybe that's not realistic, but you can see what I'm getting at, right? What we're getting at is, again, now you see that this is a model specific to this particular plant or this particular vehicle where the propulsive forces are a function of both the states and the controls, right? And here is one simple model. Now, in this case, you might say, I only see U's showing up. I don't see anything about the state showing up in this expression, right? So what we're basically saying is we're saying that this engine or this propulsion system is going to perform the same regardless of the state of the vehicle. And again, you might ask yourself, is that reasonable or is that not reasonable? It depends on what you're trying to model. So for the most part, I think this is pretty reasonable. Like the engine is probably going to perform similarly, fairly irrespective of the velocities. I mean, that's not entirely true, right? If you're going at hypersonic speeds, the engine is probably, this type of turbofan system may not be providing the same amount of thrust as it does at low speeds, but it probably doesn't care about your angular velocities or your Euler angles. It probably still performs the same, and it well, this is where it gets interesting, right? Here we're saying it behaves the same. It can still produce thrust like this. It can still produce the thrust to weight ratio of 1 regardless of where it's located in its position north, position east, and position down, which is not terribly accurate, right? Because we're saying the engine now is independent of altitude, right? So this engine is going to perform the same at sea level as it does at 10,000 feet or 20,000 or 100,000 or heck, out at the moon, right? We're saying that the engine is still going to perform the same. So again, this is just a modeling fidelity issue. If you wanted to make this more complicated, you could make the thrust, for example, start to taper off as the altitude went up, okay? So again, I think we just want to talk about this and think about the generic behavior, and we could see that, yeah, the engine or the propulsive forces realistically could probably be a function of both the states and the control inputs. Okay, so that's a general idea, and obviously this model will change depending on your actual system, but this gives us a flavor. So let's take a look at this last term in the expression. All right, so now we're on to sort of the most complicated term, and that's this term of the forces due to the aerodynamics acting on the vehicle. And this is going to be a large, complicated expression for most aerospace systems. So I again just want to give everyone an inkling of how we would start formulating these. So for example, one force that is probably acting on this aircraft, right, is lift, right? So there's a lift force. So the lift force is usually going to be something like, it's the coefficient of lift, right, times the dynamic pressure times some reference wing area, right? So this would give you the amount of lift. So this coefficient of lift, this is the complicated term. So this is usually what everyone draws. If you go to a wind tunnel and you gather data, you're going to see something like this, right? This is your classical CL versus alpha lift curve, right? So where you increase the angle of attack, right, the lift goes up and up and up until the vehicle stalls and you lose lift, right? So you can see that this right here describes what this term looks like. So one thing that we're going to need to know is what is the angle of attack of this vehicle, right? So as this thing is flying along, is it at a shallow angle of attack, a more extreme angle of attack, or is it really extreme and probably stalling, right? So this is one thing we need to be able to describe, is what is the angle of attack of the vehicle. And this is why it's so nice that we actually have the states as the velocities in the body x, body y, and body z. In other words, this is why we wanted u, v, and w in our state vector for our equations of motion, because the angle of attack, I think if you draw the geometry of it, let's draw a wing, right? So here's the wing. Let's say that the local wind is sort of coming at the wing like this. So here's your v infinity, right? That's your air coming at it and hitting it. Well, I think everyone would agree that the angle of attack is this. It's the angle that typically some reference line, usually the chord line of your wing, makes with the local wind vector, right? And what's nice about having u, v, and w is that this wind vector, when you project it onto the aircraft, assuming that we're flying in steady state air, right? There's no actual wind fields other than just the wind due to the vehicle moving through the air. The angle of attack, if you look at this long enough, you can project this and we basically get, there's a component u, right? That's the velocity of the airspeed or the ground speed, which are the same thing in this case, projected on the body x is u, and then you have w like this, right? So the angle of attack is really just going to be a trigonometric relationship between u and w. In other words, the angle of attack is going to be your a tan 2 of w and u, right? And again, I'm using the assumption here that the a tan 2 that we're looking at here needs the y component and then the x component in that order, right? So again, we had a complete separate discussion on a tan 2, which feel free to check that out if you're interested. But long story short, we see that the angle of attack here, it's really a function of states 1 and states 3, right? So the angle of attack is a function of the state vector, right? Okay, now that we have the angle of attack, that means that the lift force, right, CL, is also a function of x1 and x3, right? Perfect. Now, how about this term Q, right? So Q is your dynamic pressure. So this is what? It's 1/2 rho v squared, right? So we got to ask ourselves, okay, what are all of these terms? Well, V, that's pretty easy, right? So V, it's just your airspeed, right? So it's u squared plus v squared plus w squared square rooted, right? Or this is what? It's states 1 squared plus state 2 squared plus state 3 squared, right? So here's an expression for your airspeed, right? So you can jam that in for here, right? Now here, what about density? Rho, right? Is that a constant? Would this just be 1.225 kilograms per meter cubed, right? This is your standard sea level air density. Well, what we see is for this vehicle, we actually have altitude information. So really, the air density is probably a function of altitude. So really, this may be a better model where we should say that this is some function of x12. Right? Depending on how high you are, the density changes. So what I guess we're getting at here is you can see easily how Q is also now a function of the states. It's a function of, well, gosh, I didn't leave enough room. But I think everyone gets the point. I'm just going to write it like this. It's a function of the states, right? You need to know the speeds and you need to know the altitude in order to calculate your dynamic pressure. So all of this is to basically go and say that, look at all of this. This is a function of x, this is a function of x, so therefore the lift is a function of x, right? So the entire aerodynamic force in the body, right? So the force aerodynamic in the body frame, it's going to be, well, the x force, we got to be careful about that. What is the component in the x? If we draw our vehicle, this is like negative drag, right? Negative drag, and then the force in the y, it's the side force, whatever that is, in terms of sign, it's like that. And then the body z, this is actually negative lift, right? Again, the negative sign is to align the convention of lift is typically acting up, right? So again, maybe we should have drawn the vehicle, right? So here's your vehicle. So lift is typically acting up, right? Whereas your z body axis is down through the floor, right? So the negative sign just reconciles this. So what I'm getting at, again, I apologize for rambling, but we saw now that lift is a function of the states, right? And similarly, the side force is probably a function of the states, and the drag force is also probably a function of the states. And again, if you think about this long enough, what else could affect the lift on this aircraft? Well, this might be the lift generated by say, a normal configuration, but if you deflect some control surfaces, like you deflect the flaps or the elevator, you probably change this lift force, right? That's the whole point of flaps on an aircraft, is you increase the flaps, you increase the lift at the cost of additional drag typically, right? So this whole curve can shift up. So this curve can be a function of U as well, right? You change control surfaces and you can change this lift, right? So really, you can easily see how all of these forces are now a function of the state as well as the control vector, right? Okay, so again, what we're seeing is this aerodynamic force is really a function of the states and the controls, right? So again, this is a overly simplified, quick shooting from the hip discussion, because if you really want to characterize all of these different aerodynamic forces, right, you might need to go to a wind tunnel and do some experimentation to get what these curves look like and how they're dependent on all of these different states and controls. And again, we have in fact, that's going to be one of our next discussions, is a complete series on wind tunnel testing to figure out how we obtain all of these different relationships. But at the end of the day, we basically see that this is now a very complicated expression for all the aerodynamic forces, which are dependent on the state and the control vector and constants only. So great, that is perfect. That means we've got this thing here. Oops, sorry, I didn't mean to erase that little arrow here, right? But we now see that this is really a function of the states and the control. So here's where this control vector U weasels its way into this term F, right? Okay, so I think we talked about that. What about the moments? The moments is a very similar discussion. All right, so the moments are really similar. So in fact, what we can do is let's just change all of these F's to M's, right? So instead of looking at forces, let's now look at moments. And pretty much all of the same discussion holds true. The only difference that is maybe worth noting right here is, what is the moment due to gravity expressed in the body force, or expressed in the body frame? Well, since we're taking moments about the center of gravity of this vehicle, luckily this is just a big fat zero. So we actually don't need to worry about moments due to gravity, but still we see that yes, there are moments due to the engines or propulsion, and there's going to be moments due to aerodynamics. So again, it's the exact same discussion we just have, so I don't want to repeat the discussion, only just to say that these are a function of the states and the controls, right? And these are a function of the states and the controls, right? So therefore, this is a function of the states and the controls, and therefore we should basically denote here that this moment is a function of the states and the controls. So again, we see that both the states and the controls of the vehicle weasel their way into this one simple term MB and make this another nightmare, complicated, hideous expression. I guess maybe I shouldn't have used the descriptor nightmare. This is what makes this interesting, right? This is what makes these equations of motion specific to your complicated aerodynamic aerospace aircraft system, is that the forces and the moments are very rich, right? You're going to need very complex functions to describe them, lookup tables, all that kind of good stuff, but that's what is going to make these equations of motion accurately represent this complicated flying aircraft, right? Okay, so I think that's a good discussion of the forces and the moments. This mass is that's pretty idiot proof, right? Mass is just the mass of the vehicle. But how about this IB matrix? There's a couple of things we might want to think about when we're talking about that inertia matrix. All right, so the next thing that might be interesting to look at is this inertia matrix IB. And oh, actually, I'm noticing. Oh, shucks, sorry. There should be a minus sign here, right? This is F minus and M minus. I think I erased that minus sign when I was putting in this F of X and U and M of X and U. So anyway, just double check your notes. Make sure there's a minus sign right there. But okay, anyway, let's take a look at this matrix IB, right? And the reason I want to take a look at it is because, as you can see in the equations of motion, there's a IB inverse. And I don't know about you, but anytime I see inverse of a matrix, the first thing that goes off in my head is this thing invertible? Is it singular? Is it badly scaled? Any of that kind of stuff. So let's take a look at this inertia matrix IB. So you might ask yourself, what does this thing look like? Well, we know it's a 3x3 matrix, right? And the question is, what goes in each one of these entries? So for a lot of simple objects, like if you had a brick or a football or basically something which was symmetrical about its three planes, then what this thing is going to look like is it's just going to look like you're going to have a, you know, like an IXX, an IYY, and an IZZ, and then zeros everywhere else, right? So it'll be just a diagonal matrix with basically the moments of inertia about each axis along the diagonals. And in this case, you can clearly see that, yeah, this is no problem, right? The inverse of this is just, well, it's just 1 over IXX, right? 1 over IYY, and then 1 over IZZ with zeros everywhere else, right? So that's not a problem if your object is symmetrical. However, for a lot of systems and a lot of vehicles, like again, taking our aircraft into an example, it's not symmetrical about all the planes. Now, that being said, it is typically symmetrical. Most aircraft, right, if you draw it from a top-down view, right, I think everyone would agree that, you know, here's your body X, here's your body Y, and then body Z is going into the page here, right? So this is usually symmetrical about the X body, Z body plane, right? So you slice this thing straight down the middle. The left half of the plane is probably the same as the right half of the aircraft, right? I shouldn't say plane here because we're talking about this plane as the geometrical mathematical structure. But anyway, the left side of the aircraft is the same thing as the right side of the aircraft, right? But it is not true for any of the other planes, right? It's not symmetrical in that case. But for most aircraft, this is usually true, right? So in that case, what you end up happening with your inertia matrix is it looks similar, except now there are usually non-zero cross terms in this entry and this entry. So typically what you're going to see here is you're going to have a negative IXZ and a negative IXZ, okay? And again, the notation for what you're seeing here with this negative sign is the assumption is that IXZ is positive. Therefore, this entry and this entry are going to be numerically negative numbers. So what a matrix might look like, let's go ahead and I'll just write down a numerical value. So for example, in one of the aircraft models that we will be developing later, this matrix looks like about 40, 0, about -2. Again, I'm just putting in approximate numbers. 64, 0, -2, 0, and about 100. And all this is multiplied by the mass of the aircraft. So we're going to develop later on an aircraft model which has this type of inertia matrix. And as you can see, it's mostly positive numbers, except you have negatives on these off-diagonal terms, right? So that's what this notation is meant to represent. And again, this is an inertia matrix for a system or a vehicle or an object or whatever, which has this plane of symmetry about the X body, Z body plane. Right? So in that case, actually, the nice thing about this is, again, yeah, you can calculate IB inverse in closed form, and you take this, and actually I would run over to a symbolic manipulator like Mathematica and basically compute its inverse. And you know, let's just do a couple of these. I'll just show you, and again, like I said, you can go to Mathematica if you want to verify this for yourself. But where you get interesting behavior is here. This inverse is IZZ all over negative IXZ squared plus IXX IZZ. And then you get 0, 0, 0, 0, This entry is 1 over I, y, y. And then this 3, 3 entry is I, x, x, all over negative I, x, z squared plus I, x, x, I, z, z. Okay. There you go. And then, oh, these are symmetrical. So yeah, I'll just do this for completeness here. So I, x, z all over negative I, x, z squared plus I, x, x, I, y, y. Okay, and then this is symmetrical. All right, so it's going to be look the same as that. Okay, so here is what the inverse is going to look like. And again, if you inspect it, you can see that, you know, IYY, that's always going to be a positive number, right? Unless you have a super skinny aircraft, right? Then this is probably not going to be infinite, right? So this is okay. These terms, you might have to worry a little bit because as you can clearly see, this has a potential to kind of, this denominator could be 0, right? Under certain kind of combinations, it might be possible that this gets small. So again, you have to be a little careful in the sense that this inverse, it might be singular or it might be badly scaled or have a bad condition number, depending on the actual numerical values of, you know, all of these different moments of inertia. So luckily for most situations, this is okay. It doesn't turn out to have a poor condition number, and therefore this matrix is invertible. So that's one thing. So I think we can say, okay, that's not too shabby, okay? While we're staring here looking at this inertia matrix, maybe what might be interesting is let's look at some of these cross-coupling terms associated with this equation. Okay, what I mean by cross-coupling terms is let's examine these 3 sets of equations here. So for x4, 5, 6 dot, which was PQR dot, or as we saw earlier, you could write that as omega b with respect to I expressed in the body frame dot like this, right, with respect to the body, right? This was these 3 terms here, right, that vector. So, okay, that is given by, tell you what, let's distribute this IB inverse throughout the equation, right? So you have IB inverse times moment in the body minus IB inverse times the quantity omega b with respect to I expressed in the body frame crossed with IB omega b with respect to I expressed in the body frame, right? Okay, great. Now, if you stare at this thing long enough, you can basically see that this over here is like your angular acceleration, right? And we see that, okay, the angular acceleration, yeah, it depends on the moments, right? This is basically, like we said, this is sort of Newton's second law for rotation. It's like, instead of F is equal to ma, it's moments is equal to moment of inertia times angular acceleration, right? So this term right here is, this is the acceleration or the angular acceleration due to the external moment. Right, which again makes perfectly good sense, right? You put a moment on this object, it's going to angularly accelerate, right? So this captures that bit, right? Now, what's fascinating is this entire term here. What is this thing? So if you look at this long enough, you see that this is basically, this here is the angular velocity, right? This omega b with respect to I. So this coupled with the inertia matrix, this is almost measuring, or it's basically predicting angular accelerations that are due to rotation, angular rotation, right? So let's write that down, right? So this here, you can almost interpolate as angular acceleration due to angular velocity, right? So what does that mean? Let's expand this entire thing. And again, I am just going to run over to Mathematica and have it do this, right? Have some symbolic manipulator do these cross products and matrix multiplications, all that kind of stuff. And then obviously substitute in the fact that omega b with respect to I is just P, Q, and R, right? It's that vector. So I'm going to do that. So again, here's a screenshot of this if you want to see what it came out to be in Mathematica. You know what? Let me just write down what it it turns into, right? So this entire term, I'm just looking at this portion over here, right? That whole thing comes out to this. And I'll tell you what, let's just fast forward the camera and I'll write this down. All right, so you end up with this ugly thing. For the case where the inertia matrix is this, aircraft situation which is symmetrical about the XZ body axis. So again, I want to stress that this result is basically for, think about it as like for an aircraft or any other object where the left half of it is the same as the right half of it, okay? But not in any other plane. There's no other planes of symmetry. It's just one plane of symmetry. This is what you end up with. And again, this is kind of fascinating here because what we can do is, let's consider a case, okay? What happens if you have a really simple case of, oops, let me spell this right. Consider something like this. How about let's make all of the moments equal to 0. So there's no moments acting on this object, right? And then let's also make it so Q is equal to R is equal to 0, okay? So there's no pitch rate and there's no yaw rate, but let's make it have a roll rate. So P is not equal to 0, okay? So what that basically means is you've got this object, there's no external moments on it, so I'm not going to be twisting it or anything like that, but all this thing is doing is, for whatever reason, something has induced a roll, right? It's kind of doing this axle roll behavior, okay? So now we ask ourselves, okay, under these conditions, what do you expect to have happen? What should the angular acceleration do if there's no moment on it, right? And you might say, oh, because there's no moment, I would expect no angular acceleration. But what's fascinating is that's actually not true. If you plug in all of these conditions, right, into our angular acceleration equations of motion, well, definitely the moment being 0, that's going to knock out this entire term, right? So sure, there's going to be 0. So there's going to be no angular accelerations due to the external moment. However, this bit right here, which is the angular acceleration due to velocity, sure, Q and R are going to be 0. So a lot of these Q's and R's are going to get knocked out and all that kind of stuff. But this entire thing up here is going to reduce to, let me see, what do we end up with? Again, I'm going to do this in a symbolic manipulator because this thing is ugly. It's going to look like 0, and then this entry is IXZ P squared all over IYY, and then a 0. So this, again, is a 3×1 vector like this. So that is actually interesting. So if you stare at this long enough, what is the left side? The left side of this equation is our angular acceleration vector, right? So this is P dot, Q dot, and R dot, right? So what's fascinating is that a non-zero roll rate actually is inducing a non-zero pitch acceleration, right? So that is really kind of interesting, and this is the fact of what's coming in due to this interestingly shaped inertia matrix, is that it introduces cross-coupling between angular velocity and angular acceleration. So if this aircraft is rolling, it also, just by the fact that it has an angular velocity vector in this direction, it is also simultaneously at that point going to induce a pitch acceleration as well. So fascinating, right? Isn't that kind of interesting? So by just moving the aircraft in one axis, you actually are going to induce motion in another axis, and that's what we're seeing here with this cross-coupling situation. And in fact, what's interesting is you can do this again also with another situation of, let's do the same thing. So same thing, M is going to be 0, okay? But now, this time, let's make the pitch rate and the roll rate equal to 0, and we'll make the yaw rate non-zero, right? And then, if you do this same thing, so now what's physically going on is you've got the aircraft sitting here, and now it is yawing, right? It has a non-zero angular velocity vector in the z-axis, right? So it's trying to yaw like that. And again, you do this analysis, and what you end up with is you plug all this in. You plug in everything. The only thing that's going to be left is a non-zero r term. And what's going to end up here is this is going to be, Yeah, okay, here. 0, and then you get negative I x z r squared all over I y y, and then a 0, right? So here, again, you see that we got this odd situation that now a yaw rate also introduces a pitch acceleration, right? Fascinating. Now, the last thing that makes this even more interesting is that, again, let's do this. M is 0, and now let's make the roll rate and the yaw rate equal to 0, and we'll have a non-zero pitch rate. Okay? So now, physically, what's going on in this scenario is now the aircraft has an angular velocity vector in the pitch direction, right? Or about the y-axis, the y-body axis. And now you can almost see what's going on by just looking at the picture, right? Due to this symmetry, we actually see that all the motion should probably stay in this longitudinal plane. So if you plug this situation into here, in fact, what you end up with is, this is going to end up being all zeros, which again is kind of what you would expect, right? Is that this pitch rate, due to the perfect symmetry of the plane of symmetry and then the interesting structure of this inertia matrix, this case does not introduce any kind of angular accelerations in any of the off-axis directions, right? So that's interesting that there's cross-coupling in 2 axes and no cross-coupling in this axis. So that's, yeah, that's kind of, I think that's kind of interesting. And again, you would not see this type of behavior if you had a more simple object, like going back to the brick example. If you had a brick or you had some other object where basically IXZ was 0, you could basically see here that if IXZ, if these cross terms in your inertia matrix were 0, you wouldn't have this cross coupling, right? So this cross coupling only shows up in interesting systems where the inertia matrix has this interesting structure. So yeah, kind of fascinating behavior. All right, so there you have it. We have gone ahead and derived our flat Earth equations of motion, and we looked at a couple of examples of how this might be applied to something like an aircraft, and we looked at some of the interesting behavior and tried to get a little bit of insight into the behavior and dynamics associated with these set of equations of motion. So this, I think, is a pretty good spot to leave it for at least from the perspective of this theoretical discussion of analyzing and deriving these equations of motion. As we saw, though, is these equations of motion, while they are fairly general and can be sort of standardized and applied to a lot of different systems, in order to get it to work for your particular aircraft or your particular vehicle system, there's a lot of customization and vehicle-specific terminology and modeling that needs to be done. So in some of our future discussions, that's exactly what we're going to talk about. We're going to talk about some wind tunnel testing, about how to go about characterizing some of these forces and moments. We'll also talk about actually implementing this type of flat Earth equations of motion into a full nonlinear 6 degree of freedom aircraft simulator using a publicly available aircraft model. So if that sounds like fun, I hope we'll catch you at one of these future discussions where we'll talk about this. And like I said, I think this is probably a good spot to leave it for today. So with that being said, I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. Another way you can support these videos and their content creation is via Patreon. So the nice thing about the Patreon support method is that we actually take 100% of the proceeds the channel receives via Patreon, and we actually dedicate that towards K through 12 science, engineering, and adventures for kids and young adults. So, like I said, this is a good spot to leave it. I hope we'll be able to catch you at a future discussion where we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.